Hi, and welcome to take 47 of me trying to make my very first video. It's still gonna suck because this is super awkward because I feel like I'm talking to nobody and I'm rambling and I'm already off topic, but this seems like the best way to try to deliver some information and learn some things during our current predicament. So I'm just going to go through something small, hopefully, to wrap up what we were doing last week about the graphing and statistics, and then figure out how to go from there. So we were talking about diet and the evolution of something called salivary amylase, which is an enzyme that you need if you want to break down starch into maltose, which will then eventually be turned into glucose, which would be good if you want to get energy, right? So salivary amylase would be something that would be an advantage for any organism that eats starch on a regular basis. And that's kind of the basis of the claim that is being investigated in this activity, that human populations have adapted to eating starch specifically. And so we are going to use this kind of simple idea to think about evolution, but also to think about the statistical ways that we analyze the data, because this is going to be applied to lots and lots of other situations, not just to this one. So we started with a bunch of data. The copy number of the AMY1 gene and the amount of protein found in saliva of 25 people who are from Europe. And we made a graph that looks something like this, right? Because when you plot all the different individuals on the graph, there is a general trend being shown by this best fit line, that there is a correlation between the gene copies that you have and the amount of protein that you're going to make. And this seems to support the hypothesis that humans are going to be adapted to eating starch, because gene copy number is something that has the ability to be acted on by natural selection. And so if you get more copies of a gene, then you get more protein, and then you can eat more starch, which means you get more energy, right? But there are problems to this. This is just a statistical trend. You might notice that the dots are all over the place. And that even though as a group, you can see a general pattern, for each individual on their own, you have a hard time making a prediction about how much protein they're going to make. For example, if you knew that somebody had 5 copies of the AMY1 gene, you would probably suspect that they'd be on the low end of the spectrum, which these 3 people tend to be. But it doesn't have to be that way, because this person has 4 copies and they have a lot of protein. There's a lot of variability in the gene expression that you can't account for in such a simple comparison between just gene copy numbers, right? So as a whole, on a population level, you have some predictive ability, but on an individual basis, those predictions can break down, which is an important idea about statistics in general. So we look at the graph, we make the graph, and we see our first correlation between the gene copy and the protein. But then that doesn't really help us with the idea that certain groups would be more specialized for that. So then we get into more data where we see a comparison between high starch diet populations and low starch diet populations. Again, it's important to remember that these are populations that have historically always been low starch or high starch diets, at least for going way back into history, like 10,000 years, right? Which would give us enough time for natural selection to work and to favor the high starch, the AMY1 copy number in the high starch diet versus the low starch diet. So we want to take this data and be able to compare the two groups. And the best way to compare two groups is with a bar graph, which gives you something that looks like this, right? We want a simple, easy way to look at the two different groups. But to generate this graph, you needed to fill out a table that looks something like this. And that's not the answer. Here's the answer, right? So we need to know the sample size, 25 in each case. We can take 25 data points and condense them into one data point using something called the mean, called the average, right? Like that's the point of doing averages, is to take a lot of data points and to summarize them in a certain way. But that can lead to sampling problems, meaning that you're highly dependent on the quality of your sample. And sometimes you might randomly sample a group and randomly get a bunch of people, in this case, who have a whole lot of copies of the AMY1 gene. But other times you might randomly get a sample where you somehow get a bunch of people who don't have very many copies. And so the sample really affects the mean. And we want to measure how much that is being in effect. So that's this thing called the standard deviation, right? And so in the standard deviation, back on our formula sheet here, the standard deviation takes each individual data point, the xi, compares it to the mean, the x bar, to see the distance away, right? That's what subtraction means. We need to know its relationship to the sample size, n-1. And then there's some square roots and things in here that are just plugging in the formulas, right? But if we get that number, then we can create something called the standard error of the mean. And this will show us basically the what's called the 95% confidence interval, that if we were to do this a whole bunch of times, there's a 95% chance that our average would fall within this range whenever we were to sample things, right? So 95% confidence is pretty good. Again, that's sort of an arbitrary number, kind of like when we're doing the chi-square, but we got to pick a number. So that's what they picked, right? And so we have the means for each group. We calculated their standard deviations, and then the confidence interval is 2 standard deviations divided by the square root of the sample size, but that gives us this number, right? So again, in the end, you get a graph that looks like this. Part of doing this is to practice doing graphs. So one thing to notice is that there's a title and there's labels. That my graph is large as it can be within reason. The biggest number that I needed to get to at first seemed like it was 7.12, but then I remembered that you needed to get the bars in here. So the highest number is something like 8.3 or whatever. And so I had 40 lines divided by 8.3, and it came out to being basically that I needed to be every 5, or every 1, 2, 3, 4. Every 4 lines was 1, because 5 I needed to round it differently, would put me just out of the range. So again, it doesn't need to be perfect, but the way that I look at it is that if your top of your graph is less than halfway across the paper, then you could have easily at least doubled all of your numbers to make the graph twice as big. So notice that in my case here, that the top of the things are about 3/4 of the way up the paper. So that's generally all right. So we have our 2 bars, the average of the high starch diet and the average of the low starch diet. The high starch diet is higher. So right off the bat, when you were just looking at the mean, the high starch diet wins and supports the claim that groups that eat a lot of starch have more copies than groups who don't eat a lot of starch. Because if you don't eat a lot of starch, then there's no reason for you to have copies, and there's no selective pressure to have you evolve to have more and more and more copies, like you would if you were in the high starch diet. So again, 7.1 or whatever it ended up being, 7.12 versus 5.48. That's very simply supports the case. But then you do the standard deviations and the confidence interval, and you put those error bars on here. And as I've illustrated with the green dots here, the lowest range of the 95 confidence interval for the high group is down at about 5.9, I think. Whereas the upper range of the low starch diet is up here in like 6.3 range, right? So it is at least statistically possible that this bar should be lower and this bar could be higher, and then that would not support our claim, right? Because then the low starch people, their group would have a higher mean than the high starch group, right? And so this is where the 95% confidence intervals are important. And when, especially if you were to see a graph on the news or whatever, somewhere, where they give you a bar graph that showed a mean, but don't show the confidence intervals, don't give you the error bars, that you should at least be wondering about their sampling methods, right? And so in the end, we could probably still say that it seems like humans have evolved to make better use of starch. The answer is not quite as clear thanks to these error bars. So hopefully your graph looks like this one. If it doesn't, make sure you ask me questions through whichever means you can, and we'll get that sorted out soon. But I think that that's the end, and I don't have to do this again. Goodbye.